Hello and welcome to this presentation on mapping the mind of instruction-based image editing models using SMILE. My name is Zainab Dekhani and I'm a master research student of computer science at the University of Hull. I've been privileged to work alongside an incredible team on this project. Today, I will be presenting an overview of instruction-based image editing models, exploring the challenges of explainability in these systems, and introducing our proposed solution, SMILE. I'll walk you through the key concepts, methodologies, evaluation metrics, and the exciting result of our research. By the end, we'll also discuss how this work paves the way for future advancement in explainable AI. Let's dive in. What are instruction-based image editing models? Imagine giving simple text instructions like make this image snowy and watching your photos transform instantly. This is the power of instruction-based image editing, but like most AI systems, these models are often black boxes, leaving us guessing about how they work or why they fail. And as they are used in critical applications like autonomous driving and healthcare, the transparency of them is crucial. These models face significant challenges. They lack transparency, making it hard to debug or optimize prompts. Sometimes the results can be inconsistent, even with similar inputs. Sometimes when a command like remove the pedestrian fails, it is unclear whether the model misunderstood the instruction, lacked capability, or having another problem. Our solution, meet a SMILE, a solution that brings interpretability to this system. By generating heat maps and visual explanations, SMILE provides valuable insight into how models process commands and make decisions. With SMILE, we demonstrate the influence of each word in an instruction on the image editing process. Instruction-based image editing models have emerged as powerful tools for modifying images through natural language commands. Some examples of these areas are Instruct Pix2Pix, other Firefly, Smart Edit, and Magic Brush. These models leverage advanced deep learning frameworks to enable precise and intuitive edits. Key advancements in this field include improvements in efficiency, with models like Img2Img-Turbo allowing faster and more accurate edits. Frameworks like human-centered generative AI align models with user intent and ethical standards. In the realm of explainability, both local and global models like SHAP and LIME are widely used. Since LIME is model-agnostic, we prefer methods based on LIME for their compatibility across various image editing models. Models like SMILE, US-LIME, Bay-LIME, and others. Among these, we choose SMILE for its enhanced robustness and resistance to adversarial manipulation, ensuring more reliable and interpretable models. This makes user interaction with editing models more understandable and trustworthy. Recent advances in explainable instruction-based image editing models include some methods like DAM, visualize text-to-image relationships with attention image heat maps. PromptJump refines prompts using attention visualization, and PathChair enhances text-to-image alignment to fix inconsistencies. Another one, Evergen and his team offers example-based explanations for user-friendly insights. These innovations improve interpretability and user trust in AI-driven image editing. In this part, for showing how we can use SMILE and fit a weighted linear regression, we used a TSNE scatter plot to visualize how different keywords influence embedding in text-based image editing. Each keyword, such as sunny, rainy, foggy, or other things from distinct clusters, while sentences without specific keywords are scattered separately. This clustering demonstrates how textual inputs guide image generation. It shows that we can fit a linear regression to show that the keywords influence it. Using a smile, we further analyze these patterns with heat maps and weighted linear regression, offering a quantitative and interpretable view of how text impacts the model's output. This approach enhances transparency and trust in these models. You can see our method in this flowchart. In the context of image classification, SMILE works by breaking down an image into smaller regions called superpixels. Then it perceives these regions randomly, keeping or removing parts and tracks how the model's predictions change. By calculating distances between the original and perturbed images using a statistical measure or ECDF distance-based light Wasserstein distance, SMILE identifies which parts of the image most influence the decision. These results are visualized as heat maps, showing the key features the model relied on. In our work, we extend this idea to interpret how text instruction influence image editing. First, we feed an image and text instruction into the model. We break down the text into individual words and create perturbations by including or excluding certain words. Next, we edit the image using the original and perturbed instructions and extract embeddings of the resulting images using Dino V2. To measure the impact of these perturbations, we calculate Wasserstein distance between the original embeddings and the edited one. These distances serve as similarity scores. Next, by measuring the Wasserstein distance between perturbed and original text, we calculate weights and then fit a weighted linear regression model and extract the coefficients. This let us pinpoint how each word in the instruction contributed to the image changes. Finally, we visualize the result as heat maps. We show the influence of each word on the image edit processing. To measure SMILE performances, we use several evaluation metrics. The first of that is accuracy. As you can see in this example, during the image editing process, we use an instruction and we expect that some of the words, like make and rainy in this sentence, have the most influence on the output. In the ground truth, only certain words contribute to the final edit, represented by binary values, with 1 indicated influence and 0 indicating no effect. We compare this with the model's predicted influence, calculating the attribution accuracy. In Model 1, the attribution accuracy is 0.8, meaning the model is less accurate. It considers word U as important word in the process. In Model 2, the attribution accuracy is 1, which presents perfect alignment with the model prediction and the ground truth. For stability, as you can see in this attribution stability test, we use the same instruction. Could you please make this rainy? And introduce a small new text by adding extra symbols such as 3 hashtags at the ends. Despite these minor changes, the generative model should ideally maintain consistent attributions for the keywords, like make and rain. The similarity scores for these words remain stable across all perturbations, with values like 0.70 and 0.90. This demonstrates the model robustness in identifying the most influential words, even with noisy inputs. For the consistency measure, we ran our model multiple times with the same input instruction. Example, could you please make this raining for 3 times or more? And analyze the attributions generated in each run. As shown in this attribution consistency test, the generative model consistently assigned similar importance score to keywords like make and rainy across all 3 runs. We consider different metrics for fidelity to show how closely the surrogate model used for explainability approximates the behavior of the original model. The first one is R squared, weighted R squared metric, quantifies how well the surrogate model fit the original model's predictions, and weighted R square hat and weighted mean square error measure the square differences between predictions weighted by similarity. Weighted mean absolute error focus on the absolute differences also weighted, and calculate the average absolute and square differences respectively between the surrogate and original models by mean L1 and mean L2. In two next slides, we focus on how the operational design domain framework is used to systematically test automated driving systems, ADS, under diverse conditions. The ODD defines the operational boundaries and limitations of ADS, helping to create structured scenarios for evaluation. In the first table, we simulate environmental conditions like weather states, rain, fog, and snow to test performance under various environmental factors. In second table, we address non-environmental variables such as person-related attributes, age or gender, object variations, vehicle colors, and temporal factors like day and night scenarios. By considering these different conditions for our method, we wanted to show about safety, trustworthy, and transparency in high-risk AI fields, such as autonomous driving. In this part, we explore the interpretability of image editing models by analyzing how specific words in a prompt influence editing images. Using a fixed prompt, we applied edits to 10 different images and leveraged a smile to generate heat maps for each one. These heat maps reveal which parts of the image are most affected by specific words, helping us understand the relationship between textual instructions and visual modifications. To summarize the result, we aggregated the weights from the heat maps and create a box plot to show the distributions of each word's influence across all 10 images. In these examples, we demonstrate the influences of snowing is more high compared to another word. This slide shows the qualitative results of our model using perturbed prompts. In the 2D plot, the red dot represents the original image, while blue dots show images generated with perturbed prompts. For example, including the keyword snowing creates clear clusters of snowy scenes closer to the red point, while excluding it keeps the images further to the original. This visualization highlights how specific words in a prompt drive changes in the generated images and demonstrates the model sensitivity to textual inputs. For quantitative results, we use some metrics. For accuracy, we use metrics such as attribution accuracy, attribution F1, and attribution area under the ROC curve. Evaluate different image editing models across 10 images and also 10 prompts. As shown in the table, Instruct Pix2Pix achieved the highest accuracy, demonstrating superior performance in generating accurate and consistent edits. For stability metric, we tested this using Jacquard index across 10 different prompts by adding and removing 3 hashtags at the end of the sentence. All models achieve a Jacquard index in 0.85, indicating a strong stability in our model. For consistency, we use variance and standard deviation across 1,000 runs. We found that Img2Img-Turbo is more consistent throughout test. We compute fidelity across different scenarios to evaluate how closely the model's local behavior aligns with the global behavior. Using 30 perturbations, we measure fidelity across 3 image editing models and analyzed various metrics. The results show that Instruct Pix2Pix and Img2Img-Turbo achieved higher fidelity compared to other models. This aligned with our observations that these two models produced more reliable and accurate outputs during our testing. Next, we compute fidelity for different numbers of perturbations, focusing first on Instruct Pix2Pix and then Img2Img-Turbo. Their analysis allows us to observe how fidelity varies as we increase the number of perturbations, providing deeper insights into the consistency and reliability of these models offered under different metrics, such as weighted MSE and weighted R-square. Finally, we computed fidelity using different distance measures, including Wasserstein and cosine across the weighted linear regression and Bayline. The results show that using Wasserstein distance for both image versus image and text versus text comparisons resulted in higher weighted R-squared values, demonstrating better alignment and accuracy in capturing model behavior. In this analysis, we applied our model to three instruction-based image editing frameworks: Instruct Pix2Pix, Img2Img-Turbo, and Diffuser-Inpaint. We measured execution times for different explainability methods, including line, smile, and bayline, with 60 perturbations under consistent hardware conditions. As shown in the table, smile complexity is higher across all frameworks compared to line and bayline. This is because smile used the Wasserstein distance for text similarity calculations, which, while providing robust and detailed explanations, is computationally expensive. The complexity of Wasserstein distance scale with OND cubed, where n is the number of samples and d is the embedding size, making it significantly more demanding than cosine similarity used in line, which scale with OND. Also, smile requires more computational resources. It drives a stable and detailed explanation, making it an excellent choice for tasks where interpretability and precision are critical, despite its higher computational costs. In this section, we analyze how linguistics variations in prompts affect model explainability. We use different 60 tests across different prompts and show snow has more variations. Snowy and must snowy have more mean value. That shows snowy and must snowy maybe be more impactful for image editing process. Here, we extended the analysis to categorize keywords. The box plot highlights the distribution of influences across some groups like adjectives, verbs, and other phrases. The results show that some of the phrases are more consistent and having more influence in the image editing process. In conclusion, our work demonstrates the importance of explainability in instruction-based image editing models. Using a smile, we were able to provide detailed insights into how textual prompts influence visual outputs, enhancing transparency and trust in these systems. Metrics such as accuracy, stability, consistency, and fidelity revealed that models like Instruct Pix2Pix, Img2Img-Turbo, and Diffuser-Inpaint offer better performance supported by robust and interpretable heat maps. This research not only bridged the gap between users and AI systems, but also aligned with their broader goal of ensuring safety and compliance in high-risk AI applications. Looking ahead, there are several exciting directions for future research. First, we aim to extend our methodology to video generation models to explore temporal dynamics in explainability, like Sora and Gaia. And also, we plan to integrate attention-based techniques like DAM for deeper semantic alignment between text prompts and outputs. Additionally, we aim to further enhance the efficiency of SMILE by optimizing the computational complexity of similarity measures like Wasserstein distance. Finally, aligning these advancements with evolving regulations such as the EU AI Act, will remain a priority to ensure trustworthiness in safety and ethical AI deployment. And at the end, you can see the references. Thank you for watching this presentation.